Hey there, Mr. Sutton here, bringing you this Pre-Cal Honors 4-2 lesson on compound interest. In this one, we will find interest with different periods of compounding, and as a real-life application, we'll compare two different savings plans to see which one gives us a greater return. For our warm-up here, we're going to see if we can figure out how much you already know about interest. So pause the video and take a moment to fill in these blanks on your warm-up on your handout with as many words as you can figure out. All right, so going through each of these are all very important concepts for today's lesson. So we have the principal, which we symbolize with a P, or this A0 here, that means like initial amount. This is the money that you start with when you're investing. The interest, that's a percentage of the principal, the money that you're starting with, that the bank is going to add to your principal for leaving your money with them. It's basically the price of holding on to money. The simple interest, that's just figuring out this interest amount once for 1 year. So we can make this a little more complex if we figure it out more than once a year, or if we figure it out for multiple years. That leads us to something called compounding, which is figuring out the interest on the principal, so just like simple interest, and the interest from before. So when you compound your interest, you're no longer just getting a percentage of what you started with, you're getting a percentage of what you started with plus this other interest that you've been acquiring along the way. For our first example, we want to find the amount of money you'll have if you invest $5,000 at 4% interest compounded annually for 3 years. So you've actually done this before using A instead of P, but you've done this type of problem before. This is just a regular exponential sort of function. With that in mind, pause the video and see if you can figure this one out on your own. All right, let's see how you did. So instead of doing f of t equals ab to the t, I'm just going to write pb to the t because now we're calling that starting a value the principal instead of just a. So my starting value, my principal, is 5,000 on this one. For the b value, what do we multiply by every single year? Well, we're growing 4% per year, so we're going to multiply by 1.04. And then for the t value, we're going to use 3. So we're going to have 5,000 times 1.04 to the third power, and now it's time for the calculator. There we are, and pressing enter for that. That comes out to $5,624.32, and this is exact change here. Now the question is, this was nice that we got to get interest on our interest for the second and third years, but can we do better? So how can we do better than compounding annually for $5,000 at 4% for 3 years? We're going to compound monthly, or at least more than once a year. It doesn't have to be monthly, but we're going to go with that for this problem. So what does this actually mean? Well, what it means is we're going to take your 4% and we're going to chop it up into smaller percentages. But we're going to give you interest every single month instead of just once at the end of every year. How do we do that? We're going to start with the original formula, PB to the T, only we're going to upgrade your B value a little bit. What's the formula for the new B value? Well, I'm just going to show it to you and then we'll explain it. So the formula to find the growth factor for interest that's compounded K times a year, we're going to use the following formula. B equals 1 plus R over K, all of that to the K power. So what's essentially happening with this formula, because this looks kind of weird, is we're taking your interest rate, we're chopping it up into pieces. But after we add that to 1 and get a growth factor, which is going to be a smaller growth factor than if you just compounded once a year, we're going to take that growth factor and we're going to raise it to the K power. So you're multiplying that smaller growth factor by itself K times, however many times you're compounding a year. For this problem, for example, you're doing 1 plus the rate of 0.04, because that's what the percentage 4% is, and we're going to divide that by monthly, that means 12. And we're going to raise all that to the 12th power. So we're splitting your 4% into 12 pieces, but you're going to compound your interest 12 times instead of just once. Does that actually give you a better interest rate than if you just did once at 4%? Well, your growth factor with 4% compounded annually, that was just 1.04. Plug this into the calculator and see what we get now. So here I am plugging it into my calculator, and I'm going to do alpha y equals to get my fancy fraction here. 0.04 divided by 12 and close that parentheses and raise that to the 12th power. And when I do this, I'm actually going to store this value. This is going to be a crazy decimal. I'm actually going to store this value just so I can use it later on, and I'm going to store it as alpha A. There we go. Now I press enter, and there's my new growth factor, 1.04. I'm going to round it off after 4 decimals, 0.7. But I've actually stored this value as A in my calculator. So whenever I actually plug something in my calculator, I'm just going to use the full value, not this rounded off version. Okay, so this is actually a little bit better than the 1.04 that you would have gotten compounding once a year. So it should give us more money when all is said and done. Let's go ahead and finish this problem now. Pause the video and finish this off with the new growth factor. All right, so you should be doing 5,000 times 1.0407 and all those other decimals to the 3rd power. Let's plug that in and see what we get. So on my calculator, I'm going to do 5,000, and then I'm just going to do alpha A, and this A again, that's where I've stored that crazy decimal. Now I'm going to raise that to the 3rd power, and here's the magic. $5,636.36 if we round off. Is that better than last time? Well, let's take a quick peek back at what we got on the last example. So going back here, we ended up with $5,624 and change. So we've actually improved our total by about $12. So, I mean, it's not a lot, but it's enough for, say, lunch at the food court, right? But the question is, can we do better? And yes, we could compound daily, and then we'd be using 365 instead of 12, and we could compound by the minute, but can we do even better than that? So if we keep compounding more and more often, at some point we're going to ask the question, well, what would happen if we compounded continuously $5,000 at 4% for 3 years? And by continuously, I mean compounded an infinite number of times per year. Is that even possible? Before we can answer this question, we need to take a little bit of a detour up here. So I'm going to introduce a number to you now. I'm going to introduce to you the number E, which looks like a letter, but it's actually a constant. This is the natural base. It's a number that is equal to the following. This looks kind of crazy at first glance. Here's what's going on. We've got the expression 1 plus 1 over n to the n, which is kind of like your compounding B formula that we just saw in the last example. But we're doing this limit as n approaches infinity, which this is basically saying is as this n value gets bigger and bigger and bigger and just keeps growing without bound, what is happening to the value of this expression? And we can actually do a little experiment on the calculator. So here I am in my calculator. In my y equals, I've just put this 1 plus 1 over x to the x expression. And now I'm just going to go to the table, so second table, second graph, and see what's happening as this n value gets bigger and bigger. So initially we have 2 for an output. That's just 1 plus 1 over 1 to the 1. But as we increase the n value, the total keeps going up. But notice that it's not going up by a lot. I mean, we're up to 23 already, and we've only gone up to 2.6, and we started at 2. So I wonder what would happen if we go to table set, so second window, and instead of going up by ones, let's go by thousands. Let's see how big this thing can get. And if we go back to table now, let's see here. So we've got 17, we're at 2.6 and change. We go up to 1,017 for the n value. That's a really huge exponent. We've just gone up to 2.7 and some change. And if we keep going along these lines, at some point we keep getting the same numbers. Now these aren't exactly the same. It's just rounding off to fit in the column here. But this is a pretty consistent number. And that is actually what the value of E is it's approximately about 2.718. And it actually turns out there's an E button on your calculator. So let's just quit out of there. If you look at your calculator right here, your division symbol, if you do second division symbol, you end up with the number E. And if you press enter, it gives you that value of 2.718, which is pretty cool. But note that on your calculator, there's actually 2 E buttons. The other E button, which we're going to be using a lot more often, is on the second of the ln button here. So if you do second ln, it gives you e to an exponent. And then if you just do e to the 1, you get e. Now, why do we care about any of this? Well, it turns out the growth factor for continuous compounding, which involves an infinity here, is going to be e to whatever your interest rate is. Plugging that into our pb to the t formula, we will now have p times e to the r t for our formula. This is our continuous compounding formula. But again, this is nothing new. This is just replacing our b value with e to the r. So let's go ahead now and use this formula down here. Pause the video and see if you can get the right answer right off the bat using this formula. All right, let's see how that worked out for you. So I'm going to write, I call this the PERT formula. It sounds like a hair care product, but we've got a principal of 5,000. E is just the number E. It's on your calculator. Our interest rate now, we have to be careful. This formula takes our interest rate directly. There's no b value to calculate because e to the r is the b value. So we've got e to the 0.04 times 3. And let's see what that looks like on our calculator. So I've got 5,000, and again I'm going to do second ln to get my e to an exponent, and I'm going to put 0.04 times 3 in the exponent. Now it's important to note that your exponent has two things being multiplied together inside of it. That's what makes this work. And that is going to equal 5,637.48. Which, if you remember our last problem where it came out to, I believe, 5,636 and some change, this actually isn't that much better. I mean, this is like $1 better, the difference between compounding 12 times a year and compounding an infinite number of times a year. So what we've seen on the last three examples is that continuous compounding is going to beat out other types of compounding with the same amount of money invested for the same amount of years at the same interest rate. But here's another example. Let's say we have $1,000 invested for 10 years, and we have a choice of two plans. Plan A is 5% compounded daily, and then Plan B is 4.99% compounded continuously. Can continuous compounding beat daily compounding at a lower interest rate? Pause the video and calculate the amount of money you would have using both of these plans. All right, let's start with Plan A. So for this one, we're going to use our normal formula of PB to the T, but we're going to have to use our compounding formula for B. Since we've got 5% compounded daily, that means we're going to have to do 1 plus 0.05 divided by 360 for daily, all raised to the 365th power. And let's do that on the calculator. So here I've entered this on the calculator, and just like before, I'm going to store that whole value as alpha A so that I can use it again and get the exact decimals in there so I don't lose any money. And that comes out to about 1.0513. But again, we're just rounding this off to show people approximately what it is. We're actually going to use the exact value on our calculator. Using that now, we're going to have 1,000 times the exact version of this to the 10th power. And back to the calculator for that now. So 1,000 times alpha A raised to the 10th power gives us $1,648.66 approximately. All right, now for Plan B. Let's see if we can beat that with a continuous compounding. So for this, again, we're going to use the PERT formula. Same principle of 1,000. We're going to use e to the 0.0499 now for that interest rate, and we're still using 10 for t. Calculator time for this. And if I plug that in the calculator, that total comes out to $1,647.07. All right, let's compare these. So it looks like Plan A actually gives us more money. It was just a small difference in the percentage, and we were compounding continuously, but apparently continuous compounding couldn't really overcome this rate change. So in this one here, the interest rate wins over the compounding. So that's it for this one. Hopefully you found this lesson interesting. Sorry, couldn't resist. Till next time, Mr. Sutton signing off.